Press record. Welcome and thank you for joining us. My name is Dean Lee and I'm a professor of physics at the Facility for Rare Isotope Beams. This public talk is part of an initiative at the Facility for Rare Isotope Beams called the Advanced Studies Gateway. The primary goal of the Advanced Studies Gateway is to inspire people. We bring together researchers, innovators, creative thinkers, artists, and performers from all fields and strengthen ties between Michigan State University and the community. Today, we have the great pleasure of presenting a public lecture by Professor Laura Blecca on colliding galaxies and monster black holes. Professor Blecca is an assistant professor of physics at the University of Florida. She received her Bachelor of Science degree in Physics and Integrated Science from Northwestern University in 2005, a Master of Philosophy degree in Astronomy from Cambridge University, and a PhD in Astronomy and Astrophysics from Harvard University in 2012. She was a NASA Einstein Fellow and a Joint Space Science Institute Prize postdoc at the University of Maryland before joining the University of Florida faculty in 2017. She is a theoretical and computational astrophysicist whose research focuses primarily on the evolution of supermassive black holes and galaxies, including black hole formation, fueling and feedback, galaxy mergers, gravitational wave source populations, and the gravitational wave and multi-messenger signatures of binary black holes. If you have any questions during the talk, please type them into the chat or question and answer dialog box. At this time, it is my great pleasure to introduce Laura Blecca.
Thank you very much. Thank you for that kind introduction and for the invitation. I'm very happy to be here virtually today. I love talking about black holes and I'm excited to share some of my work on them with you today. So my research focuses on galaxy evolution and the evolution of the gigantic, we call them supermassive black holes that live in their centers. And one of the things that we're most interested in is what happens to these black holes when two galaxies collide. So I'd like to start off by talking about just what a black hole is to start with. So this is a picture of a black hole that you're seeing on your screen right now. Not much to see. And the reason for that is that black holes, like all objects that have gravity, bend the space-time that they're embedded in. And so this is the sort of 2D analog to the way that massive objects bend 3D space. So you can envision it like a bowling ball sitting on a mattress. And so in something like the sun, it will make this big dent in space-time. But then if we compress that sun down to an even smaller size, then it's the same amount of mass compressed into a smaller space. And so this is what happens at the end of stars' lifetimes, is what will happen at the end of our sun's lifetime, is that it will be condensed down in what we call a white dwarf, and it bends space-time even more strongly. But then if we could make it collapse even further so that all of its mass is condensed to a single point, then it would be a black hole. And so then we ended up with what we call a singularity in space-time. So it's basically an infinite curvature in space-time. And that's hard to conceptualize what exactly that means. And that's why there's so much interest in black holes, because they seem to, in some ways, defy the laws of gravity, but they are actually a robust prediction of Einstein's theory of gravity. So we can think of this, this idea of how black holes affect the gravity around them by starting with the concept of just escape velocity. All right, so if I jump up in the air, I'm going to fall straight back down. But if we have a powerful rocket, then we can exceed the escape velocity from the Earth and launch rockets into outer space. So for a black hole, so this is my slightly more complicated diagram of a black hole. So now we've got the single point at the center, and then I've got this sort of barrier around it, this at this distance away from the point in the center. So that's what we call the event horizon. And the definition of a black hole, if you will, is that the escape speed from the event horizon is the speed of light. All right. So if I'm outside of the event horizon, then if I have I'm going to need a rocket that's far more powerful than anything that humans have ever designed and probably ever will design. But I could, in theory, with enough energy, escape. But once I cross this event horizon, it's the point of no return, and I would need to travel faster than the speed of light in order to escape the black hole's gravity, which of course is impossible. And so that's why this event horizon defines where things go really wonky around the black hole, if you will. And so there is a common misconception that black holes are just, because of this, are just these cosmic vacuum cleaners that inexorably are sucking up everything around them. And so that's not, really the case. Obviously, this is a cartoon, but just the concept in general. If you get close enough to a black hole, then unpleasant things happen, right? You can get tidally stretched, and then if you fall into the black hole itself, then that's a bad day. But if you're staying at a further distance from the black hole and you're in a stable orbit, you don't even have to be very far away from the black hole at all. A few times the size of the event horizon is enough for there to theoretically be a stable orbit that you could be on. And then you can just happily orbit around like nothing's happening. And this is, like I said, our sun is never going to become a black hole. It'll become a white dwarf. But if we could take our sun and, just like Indiana Jones in the movie, swap it out really quick for a black hole of exactly the same mass, then, well, we would notice it because we would all freeze and die. But gravitationally speaking, we would continue to orbit around on the same orbit, just like we are now. So the fact that it's a black hole would not affect the gravitational pull of our orbit to a very good approximation, right? So the effects of the black hole's gravity bending spacetime would be small compared to just the sun. All right, so there's different types of black holes. So there's stellar mass black holes, or what we talk about when sort of the typical picture of a massive star gets to the end of its fuel burning lifetime and explodes in a supernova. And so these can be tens of times the mass of the sun, so the really massive end of stars that form. And then I said my work focuses on these so-called supermassive black holes. They form very early in the universe. We don't know a lot about how they formed, and that's one of the main research areas that I and my colleagues focus on, is trying to understand that better. But we know that they live at the centers of most galaxies, and that they are millions to billions of times the mass of the sun. And there is, in fact, one at the center of our own galaxy, which looks something like this spiral galaxy, and I'll come back to that in a couple of minutes. So I said no light can escape these black holes. How do we know they exist? Well, thankfully, even though stuff can't escape once it crosses the event horizon, it can create quite a show of fireworks before it falls onto the black hole. So many of you are probably familiar with an image like this. This is a stylized image from the movie Interstellar of light around a black hole. And a lot of the images that were produced for that movie were based on real simulations of how light propagates if it's deep in the potential well of a black hole. And so we do expect to see this shadow on a background. So what you're seeing here is light in maybe a disk of stuff that's orbiting around the black hole, and the light from the stuff that's behind the black hole is getting bent so strongly by gravity that it's actually wrapping around the black hole. And so that's what you're seeing there in this halo of light around the black hole. So we see light coming from the area around black holes. And this is true also with stellar mass black holes. They can end up with a companion a lot of the time, and they can strip off mass from that companion and form a similar disk that creates all this luminous emission as it's falling down into the black hole. And so just to give you some idea of the scale we're talking about here, and why we have these disks of stuff around black holes. So the event horizon of a supermassive black hole is roughly 10 billion times smaller than the size of a galaxy, give or take a few orders of magnitude. And so infalling gas streams are never ever going to just have a ballistic trajectory straight into the black hole. It's never going to be a direct hit. So they're going to miss the black hole and have to lose some of their angular momentum, a lot of their angular momentum, in order to fall into the black hole. And they do this by forming this disk, and then all of the stuff at different radii, different distances from the black hole, is moving at slightly different speeds. So that causes friction, and that causes the gas to heat up and glow very brightly. And so we can see these huge luminous sources from really across the universe, from the energy that gets released in this process. And just to give you a sense of somehow, so they can be as luminous as entire galaxy, and just to put numbers on that a little more precisely. So if we have 100 watts of power, that's a light bulb. The largest power station is roughly 1 billion watts. 1.21 gigawatts is, of course, the energy needed to power the flux capacitor in Back to the Future. And then if we go up beyond that, 10 to the 15 watts. Okay, so now we're talking about 1,000 trillion watts. That's approximately the power of the most powerful lasers. 10 to the 24 is roughly the power released by the most powerful atomic bomb that's ever been detonated. 10 to the 26 watts is the power emitted by our sun. And remember, just this number 10 to the 26, that's a 1 with 26 zeros after it. All right, so we're getting into some really mind-bogglingly big numbers here. 10 to 32 watts is about the maximum energy that can be produced by these stellar mass black hole binaries, the black holes that slough off the matter from their companion star and accrete it in a disk. But then if we go up to the supermassive black holes, then we can go up to something like 10 to the 37 watts, which, as I said, is about the same power that's produced by all of the stars in the galaxy combined, just from their normal stellar emission. And then if we go all the way up to 10 to the 45 watts, that's about the peak power that's released in a supernova. But that's, sustained for a matter of seconds, right? That peak power. Whereas these black holes can continue to shine for tens of millions of years at this power. Dean, is there a question?
Yeah, there's a question in the chat from Brendan Lamp. The question is, if light is considered weightless, how is it affected by gravity?
Yeah, that's an amazing question. And this is one of the things that's really counterintuitive about Einstein's theory of gravity. So if we go back to if you think about the picture where it was like the gravity bending space-time like a bowling ball on a mattress, the fact that space-time is curved is what causes that light to travel on curved trajectories. So if you think about it, like if I'm going to walk out my front door of my house and walk in a straight line, and let's say there's no obstacles in the path or whatever, if I can just keep walking in a straight line for thousands and thousands of miles, I'm not actually walking in a straight line, right? Because I'm walking on the surface of the Earth, and eventually that curvature is going to become important for my path. So the straightest path that I can take is a great circle around the Earth, right? And so that's what photons do, what light particles do, is they follow the straightest path they can. But because gravity bends spacetime, that straightest path is often curved. And that was one of the other triumphs of Einstein's theory, was when they showed that during a solar eclipse, when you didn't have the sun blinding you, that you could see light from distant stars bent around the sun in exactly accordance with Einstein's theory.
There's also a question from Jacob Watkins. Do essentially all galaxies have a supermassive black hole? If so, is there a good reason for this?
Yeah. So yeah, this is definitely right up the alley of my research. So the answer is at the more massive end of galaxies, because the galaxies come in all shapes and sizes too, then there are black holes in pretty much all of them. And that's really just sort of because of the end, we're at the end point of the evolution of 13 billion years of the universe, and so these galaxies have gone through lots and lots of evolution. They've had little galaxies merging into big ones. I'll show some movies of that in a bit. And so the odds are that you're going to have some kind of black hole there, and once it's there, then it can grow and grow and grow, right? And it's only ever going to get bigger. So when we get to the lower end of galaxies masses, then that's where it becomes really interesting, because the question, like I said, we don't know how these things formed in the early universe anyway, but they must have formed at some smaller mass than they are today. So they probably formed, and galaxies were smaller in the distant past too. So trying to understand exactly how common black holes are in these smaller galaxies is a big thing that we're trying to do to understand more about how they might have formed.
Thank you.
Yeah, good, great questions. All right. So I said that we see this really bright emission from these active black holes that are swallowing lots of gas, and a lot of times we're just seeing points of light like stars, but with very different spectra. But then black holes can also spew out a lot of mechanical energy too. So we can see these relativistic jets that come out at highly relativistic speeds and then slam into the surrounding gaseous medium around the galaxy and create these powerful lobes that we see in radio emission. It's from synchrotron emission primarily. And so these are just a few examples of radio images of that. This one is a combined image where we have optical emission from the galaxy, and then also a jet here, which is seen in radio and also in optical, which is a little bit rare, but it's one of the nearer by massive black holes like this that we have. And 87 is also very exciting, because this is what was observed recently with the Event Horizon Telescope. So you go back to that image I showed of the interstellar picture, right, where there's like the light around the black hole, and then you see that shadow. Well, a couple of years ago, the Event Horizon Telescope team managed to actually take that picture for real, right? So they're not just simulating on a computer, but actually seeing the shadow of the black hole imposed on all of the light swirling around this giant black hole nearby. So they're trying to make the same measurement now for the black hole at the center of our galaxy. So it'll be exciting to see what comes out of that. So speaking of the black hole at the center of our own galaxy, so this comes to part two of how we know black holes exist. So the black hole at the center of our galaxy is not active. It's actually remarkably quiet compared to those crazy luminous quasars that I was just talking about. But because the center of our galaxy is the nearest supermassive black hole, we can actually track the orbits of individual stars orbiting around in the central potential. And you see that black hole there that just went and whipped around there, or the star that whipped around that central unseen massive object. And so over almost 3 decades now, the star's orbits have been tracked, and you can then very precisely use Kepler's laws to constrain the mass of the object that they're orbiting around. And because these stars are so close to the center, then that also constrains the size of that object. And so it's very clear at this point that we have a black hole that's about 4 million times the mass of the sun at the center of our galaxy. And it's at the point where any theories you could come up with that could explain these observations without a black hole are something weirder than a black hole, some sort of physics that's very speculative and we don't really know anything about yet. And so if you pay attention to these sort of things, you may remember that these discoveries these observations actually won the Nobel Prize in Physics in 2020. So the prize was shared between Roger Penrose, who demonstrated that black hole formation is in fact a robust prediction of Einstein's general theory of relativity, and did a lot of foundational work on developing that theory. And then these two scientists, Reinhard Genzel and Andrea Ghez, for these observations I just described, that they've been monitoring these stellar orbits for the past 3 decades, and were able to demonstrate, as I said, to very good precision, that there is in fact this supermassive black hole at the center of our galaxy. So since we talked about the basics of what is a black hole, I want to talk a little bit about the basics of what is a galaxy. This is a spiral galaxy that looks something like our Milky Way, and it's made up of primarily dark matter, which we don't really know what it is yet, but we know how it interacts gravitationally with the luminous matter. And then we have stars and gas and dust, various molecules, and then a central supermassive black hole in most cases. And so our galaxy is the Milky Way. It has something of the order of 60 billion stars, which makes it a fairly average galaxy, not super huge, but not tiny either. And then we're sitting at a distance of about 24,000 light years from the galaxy center. And this movie here is showing you how the assembly of a massive galaxy in a computer simulation. So this is the illustrious TNG simulation, so-called. And this is one of the large simulation projects that I'm involved in. And so the main image here is showing gas density, and you see all of this flocculent structure and filaments and streams and small galaxies coming in and merging with this big one and forming this disk over time. But it's just a very chaotic, dynamic environment. You can see a zoom in of the central stellar and gas components of the galaxy. And then over here, you can zoom out and see how the dark matter density evolves, right? So we track that in the simulation too. And so you can see how the structure buildup of the gas and stars is really driven by what the dark matter is doing on larger scales. So this is a very old observation, but was basically the first demonstration that the structure on larger scales does indeed have this filamentary web-like structure and that's tracing the underlying dark matter distribution. So this was an observation made in the early mid-90s. And so basically this is showing the distribution of just galaxies that we see on the sky and then going out in further away a distance from the Earth. And so they mapped these two segments of the sky and showed how this structure is filamentary, and you have these clumps and these rarefied regions. And that agrees with what we expect for if dark matter is driving the buildup of structure in the universe through gravity. And so because of this filamentary, uneven, clumpy structure, that means that galaxies will frequently collide. And so pretty much every galaxy will have undergone one major collision at some point in its lifetime. And some of the more massive ones will have undergone even more. Here's just some images from the Hubble Space Telescope of galaxy collisions. Sorry, it's a little bit low resolution, but you can see there's just all sorts of really dramatic deformation of the structure of these galaxies that happens during these collisions when they're coming to create one bigger galaxy. So this is a simulation from my research of a galaxy collision, and the simulation data have been processed to look like the optical light that we would see looking at these with a telescope. So you're going to see this collision now. Pay attention to the reddening in the central region where there's lots of dust. And now we're comparing to a real galaxy merger image that was part of this study that we did a couple of years ago. And then we're going to go back to the simulation, and it's going to finish up. You'll see the black holes merge, or the galaxy nuclei merge and form one big black hole. You saw a bright flash. That was a big burst of emission from the black hole. And now we are left with this one galaxy, which is much more spheroidal than those two disk galaxies that we started with. So one thing just about this work, just in terms of like the science we were trying to do with this project, that reddening of that central nucleus affects our ability to see the emission from the black hole. It obscures it. And so we have to look in other wavelengths that aren't so sensitive to the attenuation by the dust. So that includes very high energy X-rays, which is what this study focused on. And then also infrared signatures. We can see that some of that light re-radiated in infrared after it gets absorbed by the dust. Whoops.
So Laura, there's another question from
Okay.
Takuji Kanamura. A question from my son, he says. Are there supermassive black holes in nebulae?
So generally speaking, no. So I mean, nebulae historically is a term that was actually used for galaxies before we knew what they were, before we knew that they were these giant collections of stars and gas that were really, really distant. They were hypothesized to be much smaller things that were much nearby, and they were called nebulae because, you know, rather than stars, they were just sort of these smeary smudges on the sky. And so now we know that what they called nebulae back then are actually these giant galaxies that are many, many, many times further away than what they were thinking of. And so what we call nebulae today tend to be those things that are much closer, and they might have enough stuff to contain a cluster of stars that's getting ready to form. But it's still a much different mass scale than the types of things that would be containing the supermassive black holes. Good question. All right, so our Milky Way galaxy is in fact headed for one of these big collisions right now. And it should occur, merger with Andromeda, in about 3 billion years. So mark your calendars. And the good news is that stars virtually never collide. You know, this looks like, you know, a big mess of stars all together, but there's just so much empty space in galaxies that the probability of two stars directly colliding is very, very small. So our solar system won't be destroyed, so it should be fine, and we would just be probably cast into some dramatically different orbit around this new galaxy during this merger. The other bad news is that the sun, of course, is aging all the time, and it is getting brighter as it does so. So by the time this merger with Andromeda happens, the Earth will have already become uninhabitable due to just the aging of the sun. But again, that's still, you know, 1 to 2 billion years out. So no need to cancel your Christmas plans. So black hole collisions, how do these actually happen? So there's, as I said, these stellar mass black holes. Many of them are born with companions. And some of them acquire them later on. And so then that provides them this natural source of something that they can accrete matter from. And then eventually, if both of them form black holes, then you can have a black hole collision. And then galaxy mergers will bring together two different supermassive black holes. And so then you can end up with a supermassive black hole collision because of that. And so I just wanted to go back to this image. This is the real galaxy merger image that was that simulation was compared to earlier on. And so this is kind of a more of a technical talk slide. Apologies for that, but I just wanted to highlight that, you know, we are able to find these ongoing mergers, and using these signatures, as I said, with these higher energy X-rays, they can see the obscured black holes. And one of the reasons this is really exciting right now is that the James Webb Space Telescope, which is due to launch later this month, is going to be the successor to Hubble, and it is going to be very good for seeing these black holes that are highly obscured but have these infrared signatures that we can detect. And also, because it sees the infrared, that makes it very well suited for seeing the very distant black holes at the sort of the beginning of when we think black holes formed. So stay tuned for some exciting results from James Webb after it launches. All right, so thus far I've been talking about electromagnetic emission, which encompasses all of these different things, right? So I talked about some radio observations, infrared, optical observations, invisible light. I talked a little bit about X-rays, right? So black hole, electromagnetic emission around black holes really spans the full range here of the types of emission that it produces. And then, as you may be aware, if you follow popular science news, there was a radically different type of emission from black holes that was observed for the first time just a few years ago as gravitational waves. So these gravitational waves are completely separate from electromagnetic waves. These are instead energy that is propagating as ripples in the fabric of space-time. So just like you drop a rock in a pond and you have ripples on the pond, gravitational waves are ripples in space-time itself. And so this is also how do we know black holes exist, part 3, because this gave us a whole nother window onto these objects. And so just to give you an idea of how this works, so this is a cartoon of Einstein's face superimposed on a balloon, showing you how the space-time the balloon is sitting in might be stretched and squeezed alternately along these right angles as a gravitational wave is passing through the space-time. Now, this is grossly exaggerated. So, percent deformation of Einstein's face is maybe of order 50 to 100% in this exaggerated cartoon. But the percent deformation on Earth by gravitational waves from a black hole merger is maybe 10 to the minus 20 something. So this number that's many zeros, a tiny fraction of a percent. So we needed a very precise experiment to be able to detect this deformation. And this is a movie just showing you how black holes, as they come together and merge, produce these ripples. So you're going to see this energy, the sort of orange scale. This is showing you the gravitational waves that come out. You'll see it intensify right as the black holes get ready to merge. And there's a huge burst at the moment of merger. And then they settle back down. There's this short ring down phase when the black holes are settling into their new configuration. And then you're just left with one more massive black hole in space. So how do these get detected? So the LIGO experiment is the one that recently made this groundbreaking discovery. And so that it uses the concept of laser interferometry. And so this is on the bottom here, again, an exaggerated cartoon showing how if you have two laser arms and a mirror is a fixed distance from them, then if a gravitational wave passes, then first this one's going to get longer, this one's shorter, and then vice versa. And that's going to happen in a sinusoidal wave-like pattern as the wave passes. And so if you can have these test masses here that'll get wiggled around by gravitational waves, then if you can measure the length of these arms at every instant time precisely enough, then you could actually see this signature. And so the LIGO experiment has these two detectors. The arms on each of them are about 4 kilometers long. One is in Washington State, one is in Louisiana. The distance between them helps with triangulating where these, any gravitational waves would have come from on the sky. I should update this slide. There are now the Virgo collaboration in Europe is another detector that's working together with the LIGO detectors now. And so the 3 of them have made detections. And now Kagra in Japan is another gravitational wave detector. So it's the LIGO Virgo Kagra collaboration is now making lots of gravitational wave discoveries. And so the original detection happened in September 2015, very shortly after they turned on the detector. And it was very exciting because this was not what was expected, that you can actually see the event in the raw data, right? So, there's some noise here, but you can very clearly see there's a burst of something happening right around this time when these two black holes merge. And so it was just phenomenally exciting. No one was expecting that the first discovery was going to be this dramatic. So this discovery won the 2017 Nobel Prize in Physics, awarded to these 3 people who were very instrumental in the LIGO experiment getting conceived and created and getting to the point where it could actually make this detection. And so, as I said, the first detection was in late 2015 and was published in 2016. And since then, LIGO has just made a phenomenal number of gravitational wave detections. So they actually just in the last couple of weeks, I think, released the second half of their third observing run results, along with this beautiful illustration of all of the different gravitational wave events. So we're looking at the mass in units of mass of the sun goes up as you go upwards on the y-axis here, and then the x-axis is just showing this distribution of all of these different sources. So you can see there's this exciting one recently that's pushing 200 solar masses, which is, we still don't know exactly where these are coming from. It's also made some detections of neutron star mergers, which are exciting because then you can have electromagnetic emission just from the collision of these two neutron stars. So that's a whole other topic for a talk by somebody who works in that area. So coming back to supermassive black holes. So we talked about stellar mass black holes and how LIGO and LIGO Virgo Kagra collaboration is observing them. So what about trying to observe these gravitational waves from supermassive black holes? Well, we do know that there is some evidence for black hole collisions that are in progress. So this is the closest separation black hole binary that we know of. They're only 22 light years apart. And this is still a very, very long way. This is not going to merge in our lifetime or even close to it. But there are lots of other experiments going on looking for electromagnetic signatures from much closer supermassive binary black holes. But of course, we also are really hoping to detect gravitational waves from them. And one way that we're planning to do this is with an experiment called LISA, the Laser Interferometer Space Antenna. And so it's a similar concept to LIGO in that it's a laser interferometer. And so we'll have these three stations rather than the two arms, and they will be launched into space. And the reason that's important is because to detect these gravitational waves from supermassive black holes, because they're so much more massive, the waves they emit are much lower frequencies. And so you have to have the arms separated by a few million kilometers instead of by a few kilometers in order to be sensitive to these frequencies. And so the tentative launch date for when it would be able to detect these supermassive black hole mergers is sometime in the mid-2030s, 2034 or thereabouts. And so we're very excited for this to go forward. There was also a Pathfinder mission a few years ago, which launched just the single satellite rather than the three of them, as a demonstration of a proof of concept of that this technology can work and can be accurate enough to make these detections. And it just knocked it out of the park. So this is this curve here is showing the sensitivity curve for how stable it can be to detecting accelerations in the mass that's hanging out in space. So this is where LISA Pathfinder was originally designed. And this is where we would eventually need to get to actually detect gravitational waves with LISA. So this is the LISA design sensitivity. And this is what the actual LISA Pathfinder mission achieved. All right, so exceeded expectations and a very robust demonstration of this technology. So we're very excited about LISA. Won't be around for a few years, but it's going to be pretty awesome when it is. And then there's another kind of gravitational wave experiment for the supermassive black holes that's going on right now and has been for almost 15 years. And that's pulsar timing arrays. So you're seeing here that this, apologies, this is such a low resolution video, but the idea here is you've got these two black holes orbiting around each other, and they're churning up this space-time. That's what the green mesh is supposed to indicate here, and creating these waves that are propagating outwards. And so I think we're going to zoom out here in a minute and show how these gravitational waves, as they come towards Earth, our Milky Way galaxy here, well, they're not just going to bend the space-time around Earth, they're also going to bend the space-time around these pulsars, which are these neutron stars that have really strong magnetic fields and act as these really precise lighthouses. So they are more precise than the best atomic clocks in terms of the precision of the pulses. And so if we can observe enough of them at different positions on the sky and do some triangulation, then we can look for deviations in the pulse arrival time that have the specific characteristic that matches with the type of deviations we expect from these gravitational waves passing between the pulsars and Earth. And so we're looking for signatures from black hole binaries that are getting close to merging but haven't quite merged yet. And the very exciting thing, oh no, what happened to this? Okay. What is going on? Picture cannot be displayed is what it says on the presenter view. All right, well, that's too bad. I'm sorry, I don't know what happened with that. The picture I was going to show you is fairly technical anyway. And so I was just going to mostly describe it in qualitative terms anyway. So basically, we are looking for correlated deviations in pulse arrival times. And so if there's no correlation that has any physical significance, then we can just look at, the pairs of pulsars, the angle between them on the sky, right? So this one has a fairly small angle. These two are almost 180 degrees apart in this illustration. And so if we look for the correlation in our signal, it should just be completely flat if there's no gravitational waves causing these deviations. And if we see an actual signature of gravitational waves from these black holes, then we should see what the so-called Hellings and Downs curve, because they're named after the people who proved that this is the signature we should expect, which sort of has this very specific curve. It dips down for black holes that are separated by roughly 90 degrees, and then goes back up in a particular shape. And so recently, the Nanograv pulsar timing array, which is the US-based pulsar timing array experiment, published a signal from their recent data release that suggests that we're starting to see that maybe. It's not a detection yet. Still don't have the significance to claim a detection, but it is starting to show some very interesting deviations from just that flat signal that look suspiciously like what we'd expect from that Hellings and Downs curve. So sincere apologies that the image itself doesn't display. I'm happy to pull it up afterwards if someone wants. And then this one, oh goodness.
So Laura, there's a couple of questions.
Yeah, let's do that.
Yeah, so Scott Schneider asked, SOHO is orbiting L1. Mm-hmm. They will not bother each other, question mark?
That's an excellent question. Yeah, so this is, there's a whole class of orbital dynamics that can figure out how to, so basically you have these libration orbits around the L1 point. So people who aren't familiar, there are some quasi-stable equilibria at special places around the Earth where, like for example, if you're in between the Earth and the Sun, then the gravitational forces cancel out in a way that makes that point more stable than other places. And we want these to be as stable as possible. So these are popular places to put satellites. And so, yes, there are different orbits that sort of librate around these Lagrange points, these quasi-stable points that are very well understood from orbital dynamics theory. And so that's how they can have more than one satellite at a given Lagrange point.
There's a couple other questions we'll go through. So anonymous attendee asks, though gravitational waves are of low amplitude because they are seemingly unending and everywhere, is there any possibility to harness them as energy sources, either terrestrial or extraterrestrial? Thanks.
That's a fun question. I love that idea. So I think, it's certainly, there are lots of things about the universe we don't understand. So I don't want to say that anything's impossible. I do think that as energy sources go, it's definitely one of the more difficult ones to think about making use of, just because, as I said, that the amount of deformation that we see, even from these really powerful gravitational wave sources like black hole mergers, is so tiny that, like, you know, it's a triumph of human achievement that we've even been able to detect them, let alone harness energy from them somehow. So it's, I mean, it's important to, you know, to, I think, be aware that, you know, they are, as the question asker said, you know, all around us all the time. Me waving my arms around, gesticulating and trying to describe things, I'm generating gravitational waves right now. Any motion of mass that's asymmetric is going to produce gravitational waves. But yeah, they're so tiny perturbations. That makes it hard.
There's one last question from Bill Robinson. He asks, after the event horizon forms, infalling mass freezes there as seen from outside. Do black hole dynamics reflect mass on the horizon, or do they act as if all mass is at the center?
That's a great question. Yeah. So mass does fall through the horizon. You know, so if you end up like a little space astronaut cartoon falling into the black hole, you know, you will go through the event horizon. You won't actually notice anything special about the exact point where you cross the event horizon. But you're going to be falling from that point onto the black hole no matter what. And so what the question asker, for those who may not be as familiar, what the question asker was referring to is the fact that if I am watching somebody fall into a black hole, then the light that is coming from them, reflected from them or whatever, is going to get redshifted as it comes to me, right? So that means that it's getting stretched. So the wavelengths that it had initially are going to get stretched into longer wavelengths that are redder. And this is the same thing that happens too, because the universe is expanding, and so we see things that are moving away from us because everything's moving away from us. The universe is expanding. And so redshift is also very important for understanding the light that we see from very distant stars. But this is like, I could be hanging out, you know, just right nearby and watching this person fall into a black hole, and they're, you know, maybe sending light signals back, their SOS signal or whatever. And I'm going to see that light be redshifted because it has to climb out of the potential of the galaxy. And it's the closer that person gets to the event horizon, the more and more redshifted it's going to get. And you can show that it does in fact get infinitely redshifted at the point that it crosses the horizon. And so you would actually never see that person cross the horizon, but they still do. It's because that light just has to go to an infinite redshift essentially to get to you, that you're never going to actually see them cross the horizon. Okay, that's a great question. So let me try to exit out of my screen share here and see if I can get my I've given a lot of PowerPoint presentations in my life, and this has never happened. It's showing up in the little that's so sad. All right. Well, this is far from optimal, but I'll see if I can show you. No, it's doing it on that too. Okay. Well, I know we're getting close to the hour anyway, and I figured we were probably going to not have time to go through all of these slides. So I'll just finish up with what we have here. And sincere apologies for this. I have no idea why that happened. So one thing that we have been working on in my group, so this is my student who recently graduated, Mohammed Sayeb, that led this work. So we are looking for triple black hole systems, right? So if two black holes come in and take a really long time to merge, then you could have another galaxy merger that brings in a third black hole before the first two have actually finished merging. And so we're using one of these big cosmological simulations to try to identify how often this happens. So we're looking at cases where there's no triple, first just one black hole merger and then another black hole. And then also cases where there's three black holes in the same system, but they don't really get close to each other. at any point in time. And then the cases where they do actually get close to each other, and you could have this three-body interaction. And that's important for gravitational wave sources because depending on the outcome of that interaction, one likely thing that could happen is the lightest black hole gets kicked out of the system. And then that removes energy from the system so the other two can get closer more rapidly and merge faster. So this, if the black holes do take a long time to merge, which there are a lot of theories that maybe they do sometimes, then triple black holes could be a saving grace because they will produce these gravitational wave sources even in the cases when they get stalled, if they do. And the image here that was supposed to be three galaxies merging together, all of which have active black holes. And that was sort of an example of one of these. Right, so you get a black hole kicked out from these three-body interactions. You can also get a black hole kicked out just from two black holes merging. So gravitational wave recoil is the phenomenon that makes this happen. So you remember that movie sort of visualizing the gravitational waves, this big burst of energy that gets emitted from the black holes as they merge. Well, if the black holes are asymmetric, unequal masses or unequal spins, or the spins pointing in a different direction, then that gravitational wave emission won't be symmetric. It'll be lopsided. And so that means that as the black holes come together, their center of mass is changing position, it's sort of spiraling. And at the moment of merger, that means that there's going to be this residual momentum, right? So a bunch of gravitational wave emission gets sent preferentially in one direction, and that imparts momentum to the black hole, just like if you have, a fire extinguisher or a jetpack in space, you're going to recoil in the opposite direction. And one thing we didn't know until people learned how to simulate black hole collisions directly with a computer about 15 years ago is that the maximum speed of these kicks could be enormous, up to maybe 5,000 kilometers per second in the most extreme case. And that's enough to eject it easily from any galaxy. So this is unfortunately not going to work. I'm so sorry. I will, yeah, I really have never had this happen in any PowerPoint presentation I've ever get. So apologies for that. So we can look for a signature. There's supposed to be a cool image here, but they're supposed to be able to look for signatures of these recoiling black holes by looking for black holes that are either shining and offset from the center of a galaxy. This would be a nice image of a galaxy here. Or we can look for kinematic signatures too. If there's gas that's swirling around the black hole close to it that stays with it when it gets ejected, then we could see emission lines from that gas is shifted from the galaxy's rest frame. And so, as I said, this figure wasn't that interesting. Don't worry, I'm not missing that much. The James Webb Space Telescope is going to be good for looking at the signatures of these black holes from how they actually formed early in the universe. And we actually see some of these that are present and exist at very high masses, less than 1 billion years after the Big Bang, which is really early. So James Webb is going to be great for trying to understand these, and in particular, trying to understand how they formed. So there's a lot of different formation models, theories out there, and they can kind of be classed by the mass of the initial seed, right? So light seeds could form when the first stars go supernova and die, and then the remnant collapses. And so that's just like stellar mass black holes forming in the local universe, but these would have been more massive. And then you could also have much heavier seeds that form directly from the collapse of gas clouds. But that probably requires some more Goldilocks kind of conditions, right? So the heavy seeds are much easier to grow to 1 billion masses by that very early time when we see them. But it's a little bit harder to know, whether we have the right conditions to actually make that happen. And then there's a class of intermediate seeds that could happen from, say, a runaway merger process between stars in a dense cluster, or maybe between black holes in one of these star clusters that could form this intermediate mass black hole. So one of the things that we're working on now is trying to develop new cosmological simulations with models that can emulate these various processes and what we think we know about them to figure out how that's going to affect what LISA will see, right? So we see LISA will be able to observe these black holes even very early in the universe when they collide. And what we want to do is know if LISA sees XYZ, what can that tell us about how they formed? So I think I will end there. Apologies again for the technical issues at the end, but thanks for all the great questions. I'm happy to take any more.
Thank you so much, Laura. That was a beautiful talk. I think all of us enjoyed that tremendously. So I'm sure there are lots of questions. So go ahead and write your questions into chat or the question and answer, and Laura will answer them. While we're waiting, maybe I can ask a question. So Laura, in your simulations, you obviously have dark matter in the simulations. Is there any evidence that if you only had dark matter, that you would have black holes formed from just dark matter? And how would that look different?
Yeah, so as far as we know, that is not a thing that occurs. And so really, what is important for all of the black hole formation channels we know of is that you have some sort of dissipational mechanism, that force that removes energy from the system, right? So the fact that you have gas that condenses into a cloud and cools and is able to achieve these very high densities because it interacts dissipationally is very important for any of these methods that we know of to form black holes. There are some theories that maybe very, 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 very soon in the first instance after the Big Bang and the period known as inflation, that there could have been some sort of instabilities that resulted in the formation of so-called primordial black holes. And so, but the the evidence for those is still, we don't really have any evidence of them per se. So that's still speculative.
So would it be fair to say that the mass fraction of a black hole is predominantly normal matter?
Yeah. So if you think about where did the black hole, where did its mass come from, then yes, I would say that the vast majority of it is normal matter, and we do actually have a good constraint on that. I mean, obviously the black hole will eat some dark matter, right? It's just gonna be passing by at some point, but it should be subdominant. A, because of this dissipational need for dissipational processes. B, because at the centers of galaxies, the baryons do dominate the density. The dark matter dominates in the outskirts. And then C, because of something called the Sultan argument. Way as far as back as 1982, the scientist named Sultan demonstrated that if you look at, to our best estimate or to best knowledge, the mass density in black holes in the local universe, and then you look at the black holes we see shining as quasars really brightly across cosmic time, and you make some simple estimates about how much black hole growth a certain amount of quasar light corresponds to, the numbers roughly match, right? It's a very heuristic argument. It's been improved upon. There's still with a lot of error bars in both directions, but basically the black hole mass density that we see is consistent with accretion dominated by quasar accretion, gas accretion from these quasar events.
Thank you. There is a question by Thomas Butner. He asks, since gravitational wave detection is still in its infancy and generally confirms the predictions of Einstein's general relativity, what are some of the long-term goals in making precision measurements that test the limits of the theory? Yeah,
this is obviously something that's really interesting for the future of gravitational wave astronomy too. One thing that I'm hopeful for when we have more years of LIGO observations, these stellar mass black holes, and in the future when we have LIGO observations of supermassive black hole mergers, there are a lot of things we might learn about the tests that we're able to do on GR. So I mean, we've already had a very good one from LIGO discovery. So they were able to put, one of the things they were able to do is put very good constraints on the fact that gravitational waves travel at the speed of light, which is a prediction from Einstein's theory. And so we know that. And if we've also seen evidence for spinning black holes, right? So that's a whole other set of predictions of GR, is like how space-time will behave when the black holes have spin in addition to their mass as a parameter. And if you have two of them coming together and they're spinning, then you can see evidence of that in the waveform, the pattern of the gravitational waves as they come in to merge. And so we've seen some that are pretty clearly demonstrating that, and that tells us something about, you know, how their spins process as they come in to merge, is another strong GR test. One of sort of the holy grails. This is definitely not my area of expertise, but that ring down phase right after the merger. So the phase right after the huge burst, and the black holes very quickly settle down into a new configuration. But there is a finite time where they're ringing down, right? There's some gravitational wave emission. And if you can do precise enough analysis on that ring down phase, that can place very strong constraints on GR and possible theories beyond GR. So as I said, that's not my area of expertise, but that is sort of one of the holy grails that experts in the field are looking towards, is being able to observe specific characteristics of ring down that are predicted by various theories.
All right. Well, thank you so much, Laura. Thank you for answering all of these questions. So
Thanks for asking them. Yeah.
So let's all thank Laura once again. And for any of you who want to stick around afterwards and just ask questions afterwards, after I close the formal part, please do so. Otherwise, thank you so much for coming, and see you next time.
Thank you.